Hello students and welcome to the lecture. So students, as we know that in the previous lecture we had started our discussion over the gravitation and that was our part 1, right? In this lecture basically we are going to talk about the gravitation and that is going to be part 2. In this lecture basically we will talk about the apparent weight of a man in a lift slash elevator, inertial and gravitational masses, satellite, orbital speed and time period of a satellite, escape speed, velocity, weightlessness, and at last we will see the summary of all of these. Okay. I hope you have revised the previous lecture before you have arrived for this lecture. As many times I have told you, it is for your own benefit. Okay. So basically, before starting this lecture, as usual, we have our small disclaimer here that we are required to understand first before we proceed further. So the disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the image. Now, let's begin with the apparent weight of a man in a lift and elevator. So, if we talk about it, so we could say, suppose there is a person who is having a mass m and he is actually standing on a weighing machine, which you have oftenly seen. That machine is actually placed in a lift or elevator that we usually use to go up and down in the places where the floors are high. Okay. The actual weight of the person equal to the mg, mass into the gravity. This acts on the weighing machine which offers a reaction R given by the reading of the weighing machine. So that's how we go by the apparent weight of a man in a lift or elevator. This is just an supposing event. Like we are supposing there is a person who is acquiring the mass m. He is standing on a weighing machine, like you can say here. And this weighing machine is actually placed in a lift. And then the actual weight of the person, not apparent, we are talking about the actual weight. That actual weight will be equal to the mg, right? And this acts on a weighing machine which offers a reaction R given by reading of the weighing machine. So this reaction exerted by the surface of contact on the person is the apparent weight of the person. Okay. We shall discuss how R is related to mg in the following different situation. Like when elevator is at rest. Now we could say that the elevator is not moving, is at rest. So what will be the equation there? So the acceleration of the person will be 0. Why? Because the elevator is at rest. Net force acting on the person will also be 0. Okay. Therefore, R minus mg is equal to 0 or R is equal to mg. Therefore, apparent weight will be equal to the actual weight. So, when the elevator is at rest, the actual weight of the person is equal to the apparent weight, or we could say the apparent weight of the person is equal to the actual weight. Okay, because the acceleration of a person is 0 in that scenario, and net force on the person that is being applied is also 0. Now, the second condition is elevator is not at the rest, it is moving uniformly in the upward or downward direction. Okay, but the moving is uniform. It means it is not going that much high, not going that much slow, but uniformly. Okay, and maybe it go in upward direction or maybe it come in the downward direction. But it is moving. It is not at the rest. It is moving, but uniformly. Again, in a uniform motion, the acceleration of the person will be 0. Okay, because the velocity is not getting changing, it is constant. So the acceleration of the person will be 0. Proceeding as in this case, 1, R is equal to mg. So apparent weight will be equal to the actual weight. Why? Why this is the same scenario as the elevator was at rest? Because of this uniform motion and the acceleration of the person is zero in this. Okay. When the elevator is accelerating upward. Okay. Now we are seeing this case. The elevator is accelerating in the upward direction. Okay. And now you can say it is accelerating. It is not a uniform. Okay. Just get your concept clear here. Not uniform but accelerating in the upward direction. Suppose a uniform upward acceleration of the person in the elevator is equal to A. Okay. So net upward force on the person will be equals to F equal to M. Right? From figure we could calculate that F equal to R1 minus mg or Ma is equal to R1 minus mg. Therefore, R1 equals to the mg plus Ma equals to mg plus A. Thus, R1 will be greater than the mg. Okay. Hence, apparent weight of the person will be more than the actual weight. So when the elevator accelerating the upward direction, always remember that the apparent weight of the person is higher than the actual weight of the person. Okay. Thereafter, when the elevator is accelerating downwards, now we could say it is accelerating, but it is having the downward movement, not upward movement. Okay. Suppose uniform downward acceleration of the person in the elevator is equals to A. Therefore, net downward force on the person will be F equal to M. F equal to M. From figure, we could conclude that F equal to mg minus R2. Therefore, R2 is equal to mg minus F is equals to mg minus Ma. Thus, R2 is smaller than the mg. Okay. In such a scenario, the apparent weight of the person is actually less than the actual weight. Alright. So far we have discussed the four scenarios. First, when the elevator is at rest. Second, moving uniformly, whether upward or downward. Third, accelerating in upward direction. Fourth, accelerating downward direction. Okay. In the first scenario, when the elevator is at rest, apparent weight will be equal to the actual weight. Second, when it is uniformly moving upward or downward, again, the apparent weight will be equals to the actual weight. Why? Because the acceleration of a person is zero. Second, when elevator is accelerating in the upward direction, it is accelerating in the upward direction, then the apparent weight is higher than the actual weight. Second scenario, when accelerating in the downward direction, apparent weight will be lesser than the actual weight. Okay, so this is the scenario. Now, in the free fall of the lift, this is the fifth free fall of the lift under the influence of gravity, which means acceleration is actually equals to the acceleration due to gravity. If you identify this small g, what we have come across while we were studying the previous lecture, that the small g denotes the acceleration due to gravity and the capital G denotes the universal constant of gravity or universal gravity constant. Okay. So now if we consider this free falling, okay, in the free fall of the lift, elevator under the gravity, A is equals to G. Okay. The acceleration is equals to the acceleration due to gravity. Then R2 is equals to M into G minus G equals to 0. Okay. Therefore, in this case, apparent weight of the person becomes zero, or the person becomes weightless in the condition of free falling. When downward acceleration is greater than g, okay, therefore acceleration is greater than g, then r2 is equals to m into g minus a, and r2 becomes negative. Got it? Now, therefore, apparent weight of the person becomes negative. Okay. In that event, the person will rise from the floor of the lift and stick to the ceiling of the lift. Why? Because the apparent weight of the person is now negative. So that's why, if suppose this is the lift, he's standing here, then he will be on the top of the lift because he is not moving aligned to the lift movement. Now, we have to talk about the inertial and gravitational mass. So if we talk about this, the first kind of the mass that we have to talk about is the case of inertial mass. So inertial mass is actually the mass of the material body which measures its inertia. Okay, that's why it is known as the inertial mass. Therefore, the inertial mass of a body is measurement of the ability to resist the change in its state of rest or the state of uniform motion along a straight line. If you remember the lecture on the Newton's laws of motion, that where we had discussed about this in detail, right? That basically there is a term inertia that we use, and inertia is actually the ability of any body. By virtue of this, the body could resist any change in its state. Okay, like if it's in rest, it will resist to move. If it's moving, it will resist to rest, right? So this is actually the inertia. All right. And when we go by the term inertial mass of body, so basically we try to measure the ability of a body to resist the change in the state of rest or uniform motion along a straight line. Got it? It is measured by applying the Newton's second law of motion, that is F equal to m into a, right? Force equal to mass into acceleration. As inertial mass of a body may be measured as the ratio of the magnitude of the external force applied on it to the magnitude of the acceleration produced in its motion. Okay, like what magnitude of external force you applied on the object and what magnitude of acceleration produced in its motion because of this external force. So this is actually known as the inertial mass of a body. Got it? Now let's move forward. So now, what are the properties of inertial mass? If we talk about first, inertial mass of a body is proportional to the quantity of the matter present in the body. Okay, like basically inertial mass is actually the measurement of the inertia, and that is proportional to the quantity of the matter present in the body. Like if the matter present in the body is in the less quantity, automatically the mass of the body will be less. And when the body having a less mass, it is easy to make it move, to make it stop, which means the external force that is being applied on an object to change its current state of motion or rest, that could be depend on the magnitude of the force that is being applied on it, and that magnitude is actually depend on the quantity of the matter present in the body. Heavier the body, heavier the force. Lighter the body, lower the force. Okay. Inertial mass of the body is independent of the shape, size, and state of body. It is mainly dependent on the quantity of matter present and not depend on shape, size, and state of body. Okay. Inertial mass is conserved during a chemical reaction and the process of physical combination. Okay. So you can say the inertial mass of a body could not be changed during any chemical reaction and any physical combination. For example, suppose if you're having two objects or two substances like A and B, these substances have gone to the chemical reaction. So whatsoever the initial mass of substance A have, whatsoever the initial mass substance B have, this inertial mass, even after this chemical reaction, will not change. That will remain as it is. Even suppose if the object A having some inertial mass and object B having some inertial mass, they got collided or physically combined. Even then, the inertial mass of A will not change, inertial mass of B will not change. Okay, that will remain conserved even during the chemical reaction and the physical combination. Inertial mass of a body is not affected due to presence of the other bodies nearby. Okay, like suppose if you have placed body A alongside the body B, any other factor of A or B could be affected, but inertial mass will not, because it is not affected due to the presence of the other bodies near it. Got it? When various bodies are put together, initial masses add arithmetically irrespective of the nature of materials of the different bodies involved. Okay, like you can say, now you have put various bodies like body A, body B, body C together. So the inertial masses of these bodies will be add arithmetically. Okay, they will not be at in respect of the nature of materials of the different bodies that are being involved in this get together, but that will remain irrespective of this fact. Okay, the inertial mass of the body increases with the speed of the body. As the body increases the speed, automatically the inertial mass of the body will be on increase. When a body moves with speed v, its inertial mass is given by m equal to m0 by under root 1 minus b square by c square. When m0 is the inertial mass of a body, when at rest, and c is the speed of light, then this could be predicted to give the material mass. The above relation is actually a consequence of special theory of relativity. It may be mentioned here that the mass is constant for a body at ordinary speed when v is smaller than the c by many times, irrespective of its position and its surrounding. However, when speed of a body v is comparable with speed of light c, the mass increases with the increase in speed and becomes infinite when velocity becomes the equality to the speed of light. So you can say generally v as multiple times smaller than c remains this. Okay, so mass of a body is remain constant. Okay, but when v becomes equals to c, mass of body start increasing, and after certain period of time it becomes infinite. Okay, so as we just get to by, the mass of a body is actually material mass of the body is actually rises with the speed of that body. Now we have the gravitational mass. So gravitational mass, what is the meaning of this? So far we have talked about the inertial mass. Now it's the time for talk about the gravitational mass. So gravitational mass, by definition, it is the mass of the material body which determines the gravitational pull acting upon. Okay, like that particular mass configuration of any material body through which it could deal with the gravitational pull of itself or any other body that is being acting upon that object. It is measured by applying the Newton's law of gravitation. The law is F is equal to G into m by r square, or F is equal to Fr square by Gm. When we apply this Newton's law of gravitation, we could measure the gravitational mass of any body. The mass m of the body so measured gives the measure of the gravitational mass of the body. The properties of the gravitational and the inertial masses are same. Okay, inertial mass is actually deals with the mass through which the body resists the state changement. Like if it is a state of resting, it will remain as rest. If it is at a state of motion, it will remain at motion. Okay, so the ability of a body by virtue of it, it could resist the change in its current state is actually the inertial mass, whereas the mass of a body through which it could deal with the gravitational pull acting upon that body is the gravitational mass. However, the two represent different concepts unrelated to each other and differ in the methods of their measurement. Okay, inertial and gravitational mass both are scalar and measured in the same SI unit kg. Why scalar? Because they only having the magnitude of mass, not having the direction of mass. And we know there are the two type of quantities, scalar and the vector. When a body only having the, or you can say when any concept having only the magnitude not having any direction, that is known as the scalar. When it's having both the magnitude and the direction, known as the vector. So inertial and gravitational mass both are scalar and measured in the same SI unit of kg. There is an important note written down over here. The inertial mass of a body is measured by studying the motion, that is the acceleration, produced by the applied force, and gravity plays no part in the measurement. On the other hand, the gravitational mass of the body is measured by the studying the gravitational pull on it, and inertia plays no part in the measurement. So you can say, however, their properties are same, but their measurement and their application is totally different. Inertial mass is actually based on the motion, on the acceleration, and gravity having no role in this measurement. Whereas gravitational mass is actually measured on the basis of gravitational pull and inertia playing no role in the measurement of it. Okay, so their application and measurement are different. However, their concept is very much similar. Properties, basically. Now, what is weight? Now, in the starting, we have talked about the apparent weight and actual weight. Now, it's the time to talk about the weight. Like, what is the weight and how it is different from the mass? So, if we go by the weight, we could say the force with which the earth attracts a body is called the weight of the body on earth. Like we know, earth attracts everything towards its center, whether it's on the surface of earth or it is in the proximity of gravitational pull of the earth. Similar things happen with the body. Like you can say, if there is any person standing over here, this person is also being attracted by the earth towards its center. And the force the earth is applying to attract this person towards sector is actually the weight of this person. Okay, so weight is actually the measurement of the force of attraction the earth is being employed to attract the person towards its center. Okay, the weight is the vector quantity. Why? Because it's not only having the magnitude but also having the direction. The direction is towards the center of the earth. Magnitude is the force that is being applied. Okay, a spring balance measures the weight of a body. Weight being a force with direction towards the center of earth. Weight of a body is equals to mass of the body into acceleration due to the gravity. By considering these two things, we have weight equal to m into g. Okay. This expression gives the relationship between the weight and the mass m of a body. Variation of weight with the gravity. Okay. Like mass is actually the measurement of the total physical quantity that is, or total quantity you can say, not physical, total material quantity that is being presented inside the body. Okay. So it doesn't matter what it's the gravity, mass will remain the same. Whatever the position of the body, the mass will remain the same because it is the measurement of the you can say materialistic quantity the body possesses. Okay. Whereas the weight is actually the force of attraction the earth is applying on the body to attract that object towards the earth's center. So weight could be varies with the gravitational. Okay. So we could say the value of G actually varies place to place on the earth's surface. It is minimum at the equator because the earth's having the low gravity at equator, and it could be maximum at poles because the earth having the maximum gravity at poles. It decreases with the altitude and also with the depth of the earth's surface. So the weight of the given body is also varies from place to place. For different planets, the force by which the body is attracted towards them will be different. Hence, the weight of the same body will be different on different places. Why? Because weight is actually the measurement of the gravitational pull that particular planet is being applied on that body. So maybe the Earth gravitational pull is lesser than the Jupiter's gravitational pull. So the same body will be of less weight on Earth in comparison with the body weight on Jupiter. Unit of weight equals to weight being a force, it's a SI unit and measured in the Newton, and CGS unit is time. Comparison of mass and weight, if we go by this, so we could say for mass, it is the measure of quantity of a matter contained in body at rest. Weight, it is a force with which the earth attracts the body. Second, mass is a scalar quantity only having the magnitude, no direction. Weight is a vector quantity having both the magnitude and direction. Mass SI unit is kg, weight SI unit is Newton. Mass is measured by physical or beam balance. Weight is measured by spring balance. Mass, it is a constant for a body and does not change by changing the place of the body. Weight is not constant for a body but varies from place to place on the Earth's surface and with the altitude and depth from the Earth's surface. Now, if we talk about the satellite, what is the satellite and all? So, there are the two types of satellite, natural and artificial. If we go by the natural satellite, a heavenly body revolving around a planet in a stable orbit is actually called the natural satellite. In our solar system, each planet is satellite of Sun. Why? Because Sun is at the center and every planet is revolving around the fixed orbit. For example, Earth is satellite of Sun and Moon in turn is a satellite of Earth. Because Earth revolves around the Sun in a perfect elliptical orbit, whereas the Moon revolves around the Earth in a perfect elliptical orbit. Moon goes around the Earth in about 27.3 days in an almost circular orbit of radius 3.8 into 10 power 8. Artificial satellite, on the other hand, put into the orbit around a planet by the human or man is called the artificial satellite. Russia, as a country, was the first to launch an artificial satellite named Sputnik first that was weighed nearly about 83.6 kgs and that got launched on 4 October 1957. Its period of revolution was 96.2 minutes and continued revolving around the Earth for 58 days. On January 31st, 1958, United States of America launched its first satellite, Explorer 1, made the important discovery of Van Allen radiation belt, a belt of electrically charged particles that is trapped in Earth's magnetic field. India launched its first satellite, Aryabhat, on 19th April 1975 from the Russian soil. Since then, India has put many satellites in various orbits around Earth. Examples are Bhaskar, Rohini, Apple, IA, IB, INSAT, IRS, etc. Orbital speed, if we talk about. So the orbital speed of a satellite is the minimum speed required to put the satellite into a given orbit around the Earth. The value of orbital speed is different for different orbits around the Earth. Like we could say m is equal to mass of Earth and r is equal to radius of Earth. A small m is equals to mass of satellite and v is equal to orbit speed of satellite. So h is equal to height of satellite above the surface of Earth. R is equals to radius of the orbit of satellite is equal to r plus h. Then v is equals to under root capital G into m by r is equals to under root acceleration due to gravity into r by n is equals to r into under root 8 by r plus n. Okay. It is clear from the equation that orbital speed of satellite is independent of the mass of the satellite, not depend on it. Depends actually on the radius of the orbit, r plus h. If the radius is lower, revolution speed will be higher. If the radius is high, the orbital speed or revolution speed will be lower. Depends upon the mass and radius of the Earth, planet around which the revolution of satellite is taking place. If the gravitational pull of the planet is higher, satellite orbital speed will be higher. If gravitational pull is lower, satellite orbital speed will be lower. The direction of orbital speed of a satellite at an instant is along the tangent to the orbital path of satellite at that instant. When a satellite is orbiting very close to the surface of Earth, which means radius is 2 times higher than the height, then r plus r is directly proportional to r and v equals to 0. Say then v0 under root gravity or acceleration due to gravity by substituting g, which is equals to 9.8 meters per second power minus 2 and re equals to 6.4 into 10 power 6 m. Re means the radius of Earth. Then we get velocity equals to under root 9.8 into 6.4 into 10 power 6 equals to 7.9210 power 3 meters second powers minus 2 is equals to 7.92 kilometers seconds power minus 1. Time period satellite, if we go by this, it is the time taken by satellite to complete one revolution around the Earth. Thus, it is t equals to 2 pi by r equals to under root r plus h by g equals to 3 pi into r plus h whole cube by g into p into r cube, where p is equals to mean density of Earth, r is equal to radius of Earth, h equal to satellite of height of satellite, g equals to acceleration due to the gravity. For satellite orbiting close to the surface of Earth, r is much more higher than the height. Then by substituting g, which is equals to 9.8 meters per second power minus 2, r is equals to 6.4 into 10 power 6 meter, and time period is equals to 5.08 into 10 power 3 seconds. That will be equal to 84.6 minutes. It means a satellite orbiting close to the surface of the Earth has a time period of revolution about 84.6 minutes. It is clear from the expression of time period that the period of revolution of satellite depends only upon height above the Earth's surface. The larger is the height of a satellite above the surface of Earth, the greater will be its period of revolution. Then we have angular momentum, L of a satellite. When a satellite of mass m is orbiting with linear speed v on the orbital path of radius r around the Earth, angular momentum is given by L is equals to mvr is equals to m by into under root gm by r into m square gm r square by half. From above equation, it is clear that the angular momentum of satellite depends on Earth, the mass of the satellite and mass of planet. It also depends upon the radius of the orbit of the satellite. Now the escape velocity or escape speed. So the minimum speed with which a body must be projected up in the space so as to enable it to just overcome the gravitational pull. It is known as the escape speed. In other words, we say that the escape speed on Earth or any other planet is the minimum speed which a body requires to move the vertically upwards direction from the surface and able to bypass the gravitational field or gravitational pull of that particular planet or Earth and never return on its own. Then it is known as the escape velocity. Mathematically, it is being represented here like you can see. The value of escape speed of a body does not depend upon the mass of the body and angle of projection from the surface of Earth or planet. Value of escape speed depends upon the mass and radius of the planet from the surface of which the body is to be projected. Clearly, the value of escape speed of body will be different for different planets. For Earth, it is 9.8 meters per second and radius is 6.4 into 10 power 6 meter. Then it will be nearly about 11.2 kilometers per second. If a body is projected from a planet with a speed of this smaller than the escape speed, then the body will reach a certain height, may either move in an orbit around the planet or may fall back to the planet because it is not able to reach this speed of 11.2 kilometers per second, that is the escape speed. If speed for the projection of the body from the surface of planet is greater than this escape speed of the planet, the body will escape out of the gravitational field of that planet and will move in the interstellar space with speed v1, which could be obtained using law of conservation of energy. Escape speed of sun is 618 kilometers per second. This is why lighter gases like H2, He, etc. do not escape from the sun's surface. Escape speed of moon is 2.4 kilometers per second only. So no gases exist on the moon because it is not capable to hold them. Relation between orbital speed and escape speed. Orbital speed is equal to under root g into r. Escape speed is equals to under root 2 into g into r. Escape speed is equals to under root 2 into v square. Thus, if the speed of satellite is increased by under root 2 times or 41.1, then the satellite will leave the orbit and will escape. Now, what is the weightlessness condition? It is a situation in which the observed weight of a body becomes zero. The state of weightless could be observed in the following situations. When object falls freely under the influence of gravity, when a satellite revolves in its orbit around the Earth such that the surrounding atmosphere does not offer any appreciable friction force, when bodies are at null points in outer space. Here we have finished the topic, not part for the summary discussion. We have talked about the concept of apparent weight and actual weight. Okay, apparent weight in an elevator, rest or moving uniformly. We have talked about accelerating downward. We have talked about free fall, downward acceleration, inertial mass. We have talked about gravitational mass. We have talked about conservation. We have talked about, okay, and we have talked about what is the weight. We have talked about the comparison of mass and weight, satellites, and also the escape speed and weightlessness also. So with this, we have finished this lecture. It is requested to all of you, kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and